Welcome back. So today we will discuss about complementary metal oxide semiconductor or CMOS. The CMOS logic family, it uses both the P and the N channel MOSFETs, and in the same circuit to realize several advantages over the PMOS and the NMOS families. What are the advantages of the CMOS? The CMOS family is faster and it consumes less power than other MOS families. And these advantages are offset somewhat by the increased complexity of the IC fabrication process and a lower packing density. And the CMOS can be operated at a high voltage, resulting in improved noise immunity. Also, the CMOS has very high input resistance and it draws almost zero current from the driving gate, and therefore its fan out is very high. Its output resistance is small, almost 1K, compared to that of NMOS. For NMOS, the output resistance value is 100 kilo ohm. So it is faster than NMOS, and the speed of CMOS decreases with an increase in the load. So first we will see the normal CMOS inverter operation. So this figure shows the circuit diagram of the CMOS inverter circuit. Okay. So, and these are the different how this circuit operation will look like at different inputs. Okay. So as you can see, the CMOS inverter, it consists of a PMOS and an NMOS. So here NMOS transistor is Q1 and the PMOS transistor is Q2. Okay. And the input, that it is connected to the gate of both the devices, and the output is taken from the drain of both the devices. So if you apply a positive supply, voltage to the, first we will consider that a positive supply voltage is connected to the source of this PMOS transistor, which is Q2. Okay. And the source of this Q1 is grounded. The source of this Q1 is grounded. For this PMOS transistor, this is source, this is gate, this is drain. For this NMOS transistor, this is drain, this is gate, and this is source. Okay. So for PMOS transistor, supply is directly connected to the source, and for NMOS transistor, source is grounded. Okay. Now, if you apply when the input voltage is low, say 0 volt, what will happen? If the input voltage is 0 volt, what will happen? The VGS2, gate to source voltage of this PMOS transistor, it will be minus 5 volt, because we have applied VDD is 5 volts. So VGS2 is minus 5 volt. And VGS1 is 0 volt, because this 0 is directly going to the gate of this NMOS transistor. So this Q2 will be on and Q1 is off. Okay. So, and this condition has been shown in this circuit. Okay. So output will be, in this condition, 5 volt. Output will be high. Now, when input voltage is 5 volt, you are applying a high input voltage now. What will happen? These VGS2 will be 0 volt, and this VGS1, that will be 5 volt plus 5 volt. So this Q2 will be off and this Q1 will be on. Okay. So this condition has been shown in this figure C. Okay. Let's move on to the next slide, which is about CMOS NAND gate. So in CMOS NAND gate, as we can see here, this figure shows the CMOS of 2-input NAND gate and the equivalent circuit for various input conditions. Okay. So you can see these two transistors Q1 and Q2, these two PMOS transistors, they are connected parallelly, while these two transistors Q3 and Q4, they are connected in series. Okay. Now let's consider when we are applying different input conditions, how my output will change. First, when A is 0 and B is 0, that means when both of my inputs are 0, what will happen at that time? These VGS1 and this VGS1 and VGS2 both will be minus 5 volt because I have applied A and B both are 0, right? So VGS1 and VGS2 both will be minus 5 volt. What will happen to these VGS3 and VGS4? These VGS3 and VGS4 will be 0 volt. Okay. So this Q1 will be on, this Q1 will be on, Q2 will be on, and Q3 will be off, and Q4 will be off. Okay. So how my circuit will look like? This condition is shown in figure B. Okay. Now you apply A 0 volt and B plus 5 volt. If you apply A 0 volt and B plus 5 volt, what will happen? VGS1 will be minus 5 volt, and this VGS2, what will happen? VGS2 will be 0 volt because this B is plus 5 volt, right? And what will happen to VGS3? VGS3 will be 0 volt and VGS4, it will be plus 5 volt. So this Q1 will be on, Q2 will be off, Q3 will be off, and Q4 will be on. And this switching circuit is shown in this figure C. In this condition, my output will be plus 5 volt, right? So what will happen now? In this next condition, if I apply A plus 5 volt and B 0 volt, what will happen? A plus 5 volt, B 0 volt. So in that condition, my VGS1, it will be 0 volt, and VGS2, it will be minus 5 volt. VGS3, it will be plus 5 volt, and VGS4, it will be 0 volt. So in this condition, Q1 will be off, Q2 will be on, Q3 will be on, and Q4 will be off. So this switching circuit is shown in figure D, and in this condition Vout will be plus 5 volt, right? Now let's look into the next condition. In the next condition, if I apply A plus 5 volt and B also plus 5 volt, what will happen? At that condition, VGS1 and VGS2 both will be 0 volt, while VGS3 and VGS4 both will be plus 5 volt. Okay. So Q1 will be off, Q2 will be off, Q3 will be on, and Q4 will be on. So this switching circuit is shown here, and in this condition the output will be 0 volt. So all the different conditions that we have applied, it is shown here in the form of the truth table. Okay. Now let's see the operation of the Cmos NOR gate. So this figure shows a Cmos 2-input NOR gate, and the equivalent circuits for the different input conditions are shown here. Okay, in B, C, D, E, these are different switching circuits. Okay. Now if I apply different input, for example, if my A is 0 volt, B is 0 volt, what will happen? A is 0 volt, B is 0 volt, and by the way, in this diagram what we can see, these two PMOS transistors Q1 and Q2, they are connected in series, and these two NMOS transistors Q3 and Q4, they are connected parallel. So when A equals to 0, B equals to 0, VGS1 will be VGS1 and VGS2 both will be minus 5 volt, right? And VGS3, this VGS3 and VGS4 both will be 0 volt. Okay, so in this condition Q1 and Q2 will be on and Q3 and Q4 both will be off. Okay, so this equivalent circuit is shown in the figure. In this condition output will be plus 5 volt, right? Now if you apply A 0 volt and B plus 5 volt, what will happen? VGS1 will be A 0 volt and B plus 5 volt. So VGS1 will be minus 5 volt, VGS2 will be 0 volt, VGS3 will be 0 volt and VGS4 will be plus 5 volt. So these Q1 and Q4, both will be on and Q2 and Q3 both will be off. Okay, and this equivalent circuit is shown in this figure C. Okay, so in this condition output will be 0 volt. Okay, now if you apply A plus 5 volt and B 0 volt, A plus 5 volt, B 0 volt, what will happen? This VGS1, this VGS1, A plus 5 volt and B 0 volt, right? So VGS1 will be 0 volt and VGS2 will be this VGS A plus 5 volt and B 0 volt. So this VGS1 will be 0 volt and VGS2 will be minus 5 volt. VGS3 will be plus 5 volt while VGS4 will be 0 volt. So this Q1, in this condition Q1 and Q4 will be off while Q2 and Q3 will be on, right? Q2 and Q3 will be on, and this condition is shown in figure D, and in this condition my output voltage will be 0. Now if you apply A plus 5 volt and B plus 5 volt, what will happen? VGS1, VGS2 both will be 0 and this VGS3 and VGS4 both will be plus 5 volt. So these Q1 and this Q2 both will be off and Q3 and Q4 both will be on, and this equivalent circuit is shown in this figure E, and in this case output will be 0 volt. So all these input combinations and these corresponding states of the transistor, which one will be on and off, and the outputs are shown here in the form of the truth table. Now we will see Cmos transmission gate. Okay, so what is a transmission gate? A transmission gate, it is simply a digitally controlled Cmos switch. Okay, when the switch is open, switch open means off, right? When the switch is open, the impedance between its terminal is very large. Okay, and it is used to implement special logic functions. Since the Cmos gate can transmit signals in both directions, it is called a bilateral transmission gate, and it is also called bilateral switch. It is used for digital and analog applications. Okay, so this figure it shows the schematic diagram and all the symbols, logic symbols of the Cmos transmission gate. Okay, so here these PMOS and this NMOS transistor, they are connected in parallel. Okay, so both the polarities of the input voltages can be switched. The control signal, this control signal is connected to the N MOSFET, and the inverse is connected to the P MOSFET. Okay. When the control signal is high, what will happen? When the control signal is high, the gate of this P MOSFET Q1 will be low, right? And the gate of the N MOSFET, what will happen? The gate of the N MOSFET Q2, the gate of the N MOSFET Q2 will be high, right? So if the input is low, if the input is low, what will happen? The VGS1, the VGS1 will be 0 volt and VGS2 will be positive. So in this condition, Q1 will be off and Q2 will be on. Okay. Now, if this input is high, VGS1 will become negative and VGS2 will be 0 volt. Okay. So Q1 will be on and Q2 will be off. So there is always one conducting path from input to the output when the control is high. Now, when the control is low, the gate, when the control is low, the gate of this P MOSFET Q1 is high and the gate of this N MOSFET Q2 is low. So, if the input is low, VGS1 will be positive and VGS2 will be 0 volt. Okay. So in this condition, Q1 will be off and Q2 will also be off. Okay. And if the input is high, VGS1 is 0 volt and VGS2 is negative. So again Q1 will be off and Q2 will also be off. So there will be no conducting path from input to output when the control signal is low. So what we can conclude from here? We can conclude from here is that when the control signal is high, the circuit acts as a closed switch, okay, and allows the transmission of the signal from the input to the output. And when the control input is low, the circuit acts as an open switch and blocks the transmission of the signal from input to the output. And this control, it acts as an active high enabling signal. Active low enabling is possible if the control is connected to the gate of the PMOS and to the gate of the NMOS.